Imagine this. You're standing on a beautiful, quiet beach. The sun's out, the water is perfectly calm. And then, in a split second, everything changes. The ground itself, the solid earth that you're standing on, unleashes a power so immense it can reshape entire continents and send waves across oceans. This is the story of that power, the story of how and why our planet breaks. On December 26, 2004, this wasn't imagination, it was reality. This was Banda Aceh in Indonesia, a bustling coastal city that, in a matter of moments, was turned into, well, this, an almost unrecognizable landscape of rubble and water. The sheer scale of the destruction is honestly hard to even wrap your head around. And the devastation didn't just stop there, not even close. The energy that was released that day was so unbelievably huge that it kicked off a tsunami that literally raced across the entire Indian Ocean. I mean, look at this map. You can see the starting point there in Indonesia, where over 167,000 people died. But those waves carried that same destructive force all the way to Sri Lanka, claiming another 35,000 lives, and even as far as Somalia, thousands and thousands of kilometers away.
So this brings us to the really big question, right? What kind of force, what on earth, could possibly unleash that much power? The answer, it turns out, is hidden deep inside the very crust of our planet.
To really understand that incredible power, we have to look at the Earth's breaking points. You see, the thing that caused the 2004 catastrophe didn't happen on the surface. It happened deep under the ocean, at a huge crack in the planet's crust. All that energy came from something called a fault. A fault is basically a giant fracture in the Earth's rocky crust, where two massive blocks of rock grind against each other. And in 2004, a huge chunk of the seafloor was violently shoved upwards by about 4 to 5 meters along one of these massive faults. Think about that, a 5-meter vertical jump. That's what displaced all that water and triggered that devastating tsunami. Okay, so what makes a fault suddenly move like that in the first place? It's definitely not random. There are these immense, totally unseen forces that are always at work, constantly squeezing, stretching, and twisting our world from the inside out. We call these forces stresses, and there are 3 main types of stress that are always putting pressure on the Earth's crust. Together, they are the engines that drive literally everything, from the incredibly slow process of building mountains to the sudden, violent snap of an earthquake. Now, here's where it gets really interesting. Each of these 3 stresses breaks rock in its own unique way, and each one creates a different kind of fault. If you can understand these connections, you've pretty much got the key to how our entire planet works. So, first up is what we call tension. This is a pulling apart kind of stress. The best way to picture it is to imagine grabbing a piece of warm taffy and just slowly pulling your hands apart. You know how the taffy stretches and gets thinner in the middle? That's exactly what tensional stress does to the Earth's crust.
Now, when that rock finally breaks from all that pulling, it creates something called a normal fault. The 2 big blocks of rock pull apart, and one of them slides down relative to the other one. This is happening right now in places where the crust is being stretched thin, like Africa's Great Rift Valley.
So, the opposite of tension is compression. This is a squeezing stress. Instead of pulling apart, imagine you're pushing 2 huge blocks of rock together. The pressure builds and builds and builds until one of them is forced to slide up and over the other. That's compression. And this squeezing motion, it creates what we call reverse faults, where one block of rock gets pushed up over another. This is the exact force that builds massive mountain ranges like the Himalayas. And, bringing it back to our story, it's exactly this kind of powerful upward thrust that caused the 2004 tsunami. And finally, we have shear stress. This one happens when forces are kind of parallel, but they're moving in opposite directions. The easiest way to picture this one is to just put your hands together and slide them past each other. That horizontal grinding motion, that is shear stress. And shear stress creates strike-slip faults. This is where those big blocks of crust slide horizontally past one another. If you've ever heard of the San Andreas Fault out in California, well, that's the most famous example of a strike-slip fault. It's the reason for a lot of the earthquakes that get out there. So let's do a quick recap, because that was a lot. You've got tension, which is pulling apart, and that creates normal faults. Then there's compression, which is pushing together, and that makes reverse faults. And finally, shear, which is sliding past, and that gives us strike-slip faults. 3 forces, 3 basic ways the Earth breaks. It's that simple. Now, the really important thing to remember is that these faults and forces don't just happen in isolation. Nope. They're all part of this massive, interconnected system that is constantly, day in and day out, shaping and reshaping the very surface of our planet.
And here it is, the whole shebang. You can actually see how these forces build the world we know. See out there in the ocean, that's a deep trench being formed by compressional stress, where one tectonic plate is being forced under another. That same system can then create volcanic mountains further inland. And that long, sharp cliff, that's a fault line, a perfect example of a fracture that separates two totally different landscapes. It's all part of one single, living, breathing system.
So, I guess the ultimate takeaway is this. The ground beneath our feet isn't static at all. It's this dynamic puzzle of massive plates that are constantly being pushed and pulled and sheared by these unbelievable forces. Which leads us with a pretty cool question to think about, right? If our planet is always moving, a million years from now, where will the next great mountain range be? Where will the next ocean form? The answer is being written right now, deep within the Earth.